So a lot of times when you get taught pKa and Ka calculations at school, it can seem really, really challenging because a lot of times in school they teach it like it's a whole new type of calculation question, but it's actually not. If you think about pKa and Ka calculations as equilibrium calculations, then the question actually becomes fairly straightforward and you actually know how to do it already. So if we have a look at this question here, it says a solution of 1 mole per liter dilute carbonic acid is placed into a beaker. Determine the pH of the solution at equilibrium, assuming the solution is left at standard lab conditions. And they give you the Ka value of carbonic acid at 25 degrees Celsius. So as a sort of quick recap of what Ka is, remember Ka is your acid dissociation constant. So that's a special name that they give for it. But essentially, think of the Ka value as the equilibrium constant for an acid dissociating. So what I mean by that is, we have this calculation question here. We always start off our calculation with an equation. So if we have a look at carbonic acid, it's H2CO3, and the carbonic acid dissociating, the equation should look something like this. So it should be H2CO3 reacted with any water present in equilibrium to become H3O plus HCO3 minus, like so. Okay? So essentially, carbonic acid is behaving like a Bronsted-Lowry acid, because remember it's proton donating to become the H3O plus that we see there. And then the Ka value that they've given us for this equation is 4.4 times 10 to the negative 7. So our Ka value for that is 4.4 times 10 to the negative 7. Okay? So before I said the Ka value is our acid dissociation constant. But you can also think of it as essentially the equilibrium for this equation here. Okay, so this is specific for carbonic acid, but it applies to any single Ka calculation that you do, where you think of the Ka value as the equilibrium constant for this question here. Now, the reason why there's an A there is because it's simply the equilibrium constant specific for an acid dissociating, right? And sometimes you might have Kb, which is essentially the equilibrium constant for a base dissociating, right? So A for acid. Now, how do we do this question? Well, we think back to pH. When we measure pH, we know the formula for pH is negative log base 10 concentration of H plus, right? So we really want the concentration of H plus or H3O plus at equilibrium. Now, to do that, we first draw up an ICE table. So for this equation here, we draw up an ICE table, ICE, initial constant equilibrium, and then I like to just draw a line down the middle to divide our reactants and products, right? And it's important that we go back and fill in our states. So that's aqueous, liquid, aqueous, aqueous. Okay. And the reason why it's important for the states is because obviously water is a liquid, and so we don't really need to worry about this column. Okay. So let's just try and fill out this equilibrium table now. So we know that there was initially 1 mole per liter of dilute carbonic acid. So initially we know that there's 1 mole per liter. We don't really have to worry about the water, so we can leave that out. So we know that, and then we know that the H3O plus and the hydrogen carbonate ion, they don't tell us anything about that, so we just assume there's 0 and 0, okay? Now, the next thing is determining what we want to find. Now, they want us to find the pH at equilibrium, right? And remember how we said the pH is the concentration of the hydrogen ion, right? So essentially what this question's asking us to find is they're trying to get us to find this equilibrium amount here, right? We want to find out essentially how much hydronium or H3O plus ion there is at equilibrium, which is the same as the H plus ion. So we can write those either way, okay? But we want to find this number here. Now, if you think back to equilibrium, this is essentially just a straightforward equilibrium calculation. Why? Because we know our Ka value. So if I just cover up the A, that's essentially our K value or equilibrium constant. They've just put an A, like I said before, because it's the equilibrium constant specific for an acid dissociation. Right, so let's just rewrite our Ka at the bottom here again. So that's 4.4 times 10 to the negative 7. And if I said, okay, come up with the equilibrium expression for this equation here, you should be able to do that if you've done module 5, which is the concentration of H3O plus times the concentration of HC3O minus all over the concentration of H2CO3. And we don't have to worry about the water because that's liquid, okay? And so we need the equilibrium amounts of this. Right, and so obviously we don't know that yet, but we can find it. And the way that we can find it is by introducing an unknown variable. So we if you think back to equilibrium, you introduce an x, right? So we don't know what our changes are. So let's just say that's minus x, right? So it's going to go down by a little bit. We don't know how much. And then if the reactants go down, then the products are going to go up in concentration. So that's going to be plus x. And I've forgotten to put a 0 there. So we start off 0 there. So then the equilibrium amount is going to be 1 minus x. This is going to be x. So I'll just get rid of that and put an x in, and then put an x in like that. So then now that we've come up with our equilibrium expression, we can then sort of start to sub in our equilibrium value, which is sort of this row here. Now subbing that into our formula, let's just rewrite it. We say, okay, Ka is equal to 4.4 times 10 to the negative 7, which they've given us. And that's equal to the concentration of H3O plus at equilibrium, which we know is X, and then the concentration of hydrogen carbonate at equilibrium, which is also X. So it's just going to be X squared, like that, over the concentration of HCO3 at equilibrium, which is 1 minus X. So we'll just pop that in there. Now, for those of you who are really good at maths, you could probably solve this using quadratic, but the thing about chemistry is you don't need to use a quadratic because the course is designed for people who may not even do maths. So in order to solve this question, you actually have to do something that's mathematically incorrect, but it helps us solve the calculation, and I think at the end of the day, it doesn't really make a difference. So to solve this question, what we do is we say, okay, this minus x bit here, which comes from here, we assume that's negligible, right? Because if we don't do that, you're going to bring this over to the other side, you're going to have a quadratic, it's going to be very painful to solve. So we just say this minus x is negligible. And the reason why we can say that is because carbonic acid is actually a weak acid, right? We know it's a weak acid if we've learned our strong acids, weak acids. But we can also tell that from our Ka value, right? So we know the Ka value, if you look at this Ka value, it's really small. And what does a small Ka value mean? Or what does a small equilibrium constant mean? Well, it means it lies really far to the left. It means this top bit at equilibriums, there's quite a low number of it or low concentration of it, and then the bottom bit there's a lot, meaning it doesn't really dissociate. And so to solve this question, or to make it easy for us to solve this question, we just assume this negative x is negligible. Okay, and the reason why we assume it's negligible is we're saying, okay, it's a weak acid, so the amount that it dissociates is actually very, very small, to the point where it doesn't matter for our calculation. Now, mathematically, that's not correct, but if I get you guys to in your spare time, plug this into Wolfram Alpha and solve for your x here, you'll see that it's actually very similar, if not the same, to the x that we're about to find. Okay, so if we assume that's negligible, it means we can get rid of it. So let's get rid of it. Okay, and so we're left with a pretty easy equation to solve. So the equation we're left to solve is 4.4 times 10 to the negative 7 is equal to x squared. Okay, and then you just square root everything. So x is essentially equal to 0.000663332, etc. Right? So if you just plug that into calculator, try and write out all the digits. Okay, and so that's our x value, right? So it's saying at equilibrium we have this number or that concentration of H2O plus ions, as well as that concentration of HCl3 minus ions at equilibrium. Okay, so we're not done yet. So we found our x value, which is really good. So it tells us the concentration of the hydronium ion and the hydrogen carbonate ion. But that's not answering the question. The question wants us to find actually the pH of the solution at equilibrium. So the final step is actually just really straightforward. So to find our pH, we just take this number. And the reason why we just take this number is because this number represents the concentration of the H3O plus at equilibrium. Okay, and that's what we're interested in to find the pH. So because we already have that number, which is this thing here, right? So that's the same number there. We plug that in there, right? So to find the pH, it's just going to be pH equals to negative log base 10, the concentration of the H3O plus ion, which is the same as the concentration of the H plus ion, right? So they mean the same thing, right? And then plugging that in, that's going to be negative log base 10 of 0.000663332, etc. Okay, and I just want to make this clear. It's the concentration of H2O plus at equilibrium, right? It doesn't really matter, but that's just to be technically correct, right? And then once we've plugged that in, then we plug that into our calculator, and we should get 3.1782, etc. Right? So we'll leave that there, okay? And before we sort of breathe the sigh of relief and say we got the answer, just make sure you double check what the rounding is, okay? So the general rule for rounding, which is really important because you can lose marks in an exam for this, anything you do pH with that you round to decimal point. The decimal point that you round to should be the same number of sig figs in the question. So the lowest number of sig figs in the question. So we've got 3 sig fig here, and then we've got 2 sig fig here, right? So because we've got 2 sig fig here, we should round this to 2 decimal point. So what that is 3.18 to 2 decimal point, okay? And that's our pH, right? And so we can do a quick sense check because this is carbonic acid. So obviously we know it's an acid. pH should be less than 7, and we see this number, it is less than 7. So that does make sense, okay? So to recap, how we do pKa calculations, the first thing is with all calculations, you should write up an equation. And then we say, okay, look, our Ka value is actually just the equilibrium constant for an acid dissociation equation, right? Because it's A for acid, right? So it's the equilibrium constant for the acid dissociation question, right? So it's the K value for this equation here, right? And we want to find the pH at equilibrium. So to find the pH at equilibrium, we essentially want to find the concentration of H2O plus at equilibrium, right? Which is this X value here. And once we've sort of understood that, that just looks like a very straightforward equilibrium calculation, right? So we put in what we know initially. So we know it's 1 mole per liter. We don't worry about water because it's liquid, and then we put 0 for the initial amount. Then we're trying to find the equilibrium amount. So we substitute the changes with X's, right? Because we don't know what the changes is. That's minus X plus X plus X. Just be aware of the mole ratios, right? So it's all 1 to 1 to 1. So that's why it's the same X's. And then we come out with our equilibrium amount, right? So like I said, Ka is the equilibrium constant for the dissociation of acids. So we just plug that number there. We come up with our equilibrium expression, plug everything in, okay? And then before we solve for X, we say, okay, the minus X here at the bottom is negligible. And that's purely done to make our calculation easier, right? Mathematically, it's not correct. But after this question, what you can do is you can go to Wolfram Alpha and you know, plug this in and see what X value they get. And it should be really, really similar to this number here. It might be off by a few significant figures, but you know, it's supposed to be relatively similar. So we assume that's negligible, so we can solve it. We solve for X, we get this number here, and that's saying, okay, at equilibrium, we have that number of H2O plus ions, and then that number of hydrogen carbonate ions, right? Because they're both X. And then finally, to find the pH, we just plug it into our pH formula. So negative log base 10 of H2O plus, plug it in, and then we get 3.18. And we've rounded it to 2 decimal place because the lowest number of sig figs here is to 2SF. And that's pKa calculations.